Thank you for joining us for today's webinar on optimizing glTF using geometry, textures, and workflow. Our presenters today are Paweł Nikiel and Max Limper from DGG, Andreas Vasilakis from Phasmatic, and Adam Morris from Cesium. First, a couple of housekeeping items. If you have any questions during the presentation, please ask them using the Q&A feature located on your Zoom toolbar at the bottom of your screen. We are recording this webinar, and we'll share the link along with the slides and the recording later this week. At the end of the session, please complete the short survey form to help us better design future events. With that, I'll hand it over to Paweł Nikiel, CTO of DGG. Paweł?
Hey, thanks, Jeff. So, as mentioned, my name is Paweł. I'm CTO at DGG. We're creators of Rapid Compact, the optimization software. I'm a contributor to 3D covers in 3D format working groups for Kronos. I have over 10 years of experience in 3D art, virtual and augmented reality development. I'm focused mainly on pipelines, automation, and scalable delivery of 3D content. And I like to play or create anything has anything to do with interactive. So if we move forward first, first I would like to start with saying why do we even talk about optimization here, and then what's the goal? So as you know, in 3D content production, we usually create source assets that are very well suited for animations, offline CGI production, hero shots, renders, and anything that has to do with big computing power and high visual quality, right? Like IKEA catalog or any other brand catalogs for years are now, they're not photos, they're renders of 3D assets. However, those assets are not well suited for real-time use cases. So with all the new technologies, with mobile being at everyone's pocket, and with even newer things like AR through the mobile or through glasses, virtual reality, web configurators, room planners, and so on and so forth, there is a need for more lightweight assets that run well real time. So you don't have, if you're working real time, you don't have like 5 minutes or even 5 hours to render one frame, one image. You have to render them in a matter of milliseconds to get a seamless, fluent experience. So now the way to go from one to another, of course, you can go about it manually. So you can take each asset and try to manually reduce number of polygons and convert the materials and so on and so forth. But if you imagine, of course, big scale, that it's just it's impossible to have a catalog of 10,000 products manually converted from CGI assets to real-time ready assets. Now, the way to go there automatically is, first of all, by having an asset, that source asset that's suited for automated conversion or compacting, right? So not every properties in materials, for example, are easily translatable to texture-based materials that are often used in game engines or in real-time production, like in web viewers or mobile. So there are certain guidelines that are best followed when creating the source asset to ensure that your asset can be automatically translated to something that's more consumer-facing. And for that, as a Kronos group, we created asset creation guidelines, which is this big rule book of guidelines that you should follow, or you're encouraged to follow, to make sure that your assets comply with those standards and are easily translatable to something publishing friendly. Now, if we go, please, to the next slide, we will see that different publishing targets, they have different technical requirements in terms of file size, polygon count, texture resolution, and they, of course, depend on few factors like the internet bandwidth on your target device. They depend on the hardware that you have. So, of course, mobile devices tend to have less memory, for example, than your regular PC. and there are multiple metrics that you need to target with each platform. And it's worth mentioning that, of course, we have some numbers here that should give you good performance. However, this is always a moving target, right? Like the hardware evolves, also the graphical engine evolve. So it's not that you can create one asset and one optimized asset and it stays like this forever. You can progressively push it to the limits, so you can also get the best possible at the given point in time and hardware, best possible visual quality even on those lower end devices. That's why it's very important to have this source asset again prepared in a way where, let's say, new mobile GPU comes out that allows for bigger texture resolutions, for example, or more triangles on the screen, then you can just retrigger automation process with those different metrics and get again your target output model instead of redoing everything manually, right? Now I will take you through high-level high-level steps that you would usually follow on the next slide, that you would usually follow when creating an optimized version of your asset, and then I will talk a bit more in detail about geometry optimization specifically, and a bit about animation as well. So on a high level, in terms of the workflow, first thing that we would do would be scene flattening. So if you have your, let's say, your sofa that has a lot of tiny pieces and it has cushions and has legs and like some base and everything, it's probably in your original scene where that's used for very detailed render shots. It's most likely separated and it's all nice, you can assemble it. However, for real time, of course, the less objects we have on a scene, the better, because it impacts number of draw calls. So how many times a model has to be rendered before it's actually displayed on the screen. So we like to flatten the scene, so merge those together. Then in the next step, you would go to animation optimization. Again, like if you have high resolution animation, for example, then those tiny details in smoothness of transitions, they matter. However, on your mobile device on a small screen, you can get away with bit sharper curves, for example, or a bit more compressed animation data, and you can still get a good enough result. Then we would move forward to geometry optimization. This is like the rest of my presentation, so I'm going to skip this one at this high level overview. And then we would have the UV unwrapping. So of course, after we optimize geometry, we need to create flat set of UV so that we can then properly texture the asset and apply materials to it. Then we would do the actual baking, which is translating those materials into those newly aligned texture layouts, sorry. And then at the last step, if your target device supports it, you might also compress the asset. So you can use something like Draco or some other tool to get even smaller file size in the end, so that it impacts the bandwidth, of course. So like the less data you have to download, the better. Of course, it comes at a small trade-off, because then you have to uncompress data on your target device, but the internet bandwidth is faster, right? Because it's smaller file size is better for this purpose. So can we please move forward? So I'll talk now briefly about three main techniques of optimizing geometry. The first one will be clustering. This is the oldest one. It's originated roughly in the 80s. It's very performant, very fast. It can be parallelized, so you can have different parts of assets optimized at the same time, because in the end they don't impact each other. Now, when would you use it? It's usually used with the huge data sets and very dense meshes, because it's not very pretty. Like the results are not as accurate as you can get with the two following techniques I'm going to talk about. However, since you can parallelize it, it's very, very fast. And when you need to save memory, or for example, sometimes in game engines, when you have to real-time optimize geometry depending on the distance, when you don't have predefined LODs of your asset, but you actually want to real-time change maybe a very dense meshes into something smaller, then you might use this one. And the way the optimization happens is essentially, as you can see on this diagram, you just split the model into a cube essentially and the cube into smaller boxes, and then for each of those boxes you just find one point that is representative, which is like an average of all the points that are included in this box, and you merge everything to this one point, right? So that's why you can see that it can be parallelized because they're independent from each other. You basically find one point for each cube, and there you have it. And this is the first technique, as I mentioned, like the first one in computer science probably. However, like I mentioned, it's not very accurate right now. It only makes sense with super high dense meshes. And if we move to the next slide, you can see this nice statue that used to be a 3D scan, very dense. And then, for example, to perform some optimization on mobile, maybe this could be used as a technique so that you can actually get something optimized, but you don't have to waste too much resources, right? Then if we please move forward. Second technique I want to mention, and this is probably like, decimation is a word that most likely many of you know. It's often featured also in 3D applications like Blender or Max. And decimation is a very well-established technique. It's different from the clustering. It's a bit more modern, but like it started also probably somewhere around the 90s. It is a sequential technique, so it happens step by step. So it's not that easy to parallelize. However, it's possible, depending on how accurate you want to be with your results. It's possible to tweak the performance versus accuracy. So if you need high performance, maybe you don't care that much about accuracy, you can set basically how much do you check your output, and if you don't care about performance that much and you want accuracy, you can tweak it this way, and I'm going to mention in a moment what does it actually mean. Now, when would you use this technique? It's often used when you have good input topology, or you have 3D scans. Basically, you have something that's fairly nicely done up front. So it can be dense, it can be high poly, but it doesn't have many artifacts. It's very well suited when you want to have specific number of triangles. Like I showed that there, for different target platforms, you might have different triangle outputs, different polygon outputs needed. So with this technique, you can specify to a triangle literally how many of those you want to have in the end, because again, it happens sequentially. So you always can keep track. You can always keep track of how many you have so far. It's very well suited when you need to preserve data. So for example, if you have high poly asset and you have your UV layout that you want to reuse, this is a good technique to use, because you optimize the mesh, but you stay in the same bounds, and you know always what you do with your topology to make it smaller. It's not well suited for noisy meshes or high genus. So like if you have a mesh that has a lot of holes, this technique most likely will break it. You can get some artifacts. Of course, to some extent, you can always use it. But if you want to go extreme with your poly count, like extremely low, or just way lower than the input format, than the input number, then you're likely to break your geometry this way. It also doesn't work very well with overlaid layers. So if you can imagine a parallel and you have like multiple layers stacked quite close to each other, you can also get some artifacts. Now there are ways to work around it, or there are algorithms that allow you to still keep them separate, even though you would decimate the mesh. But in most scenarios, this is likely to produce you some artifacts that you obviously don't want. And the way the actual optimization happens is you calculate quadric error or edge length, which is just the way of finding let's say the new position of your target vertex that has the smallest or the target edge that has the smallest offset from the original curvature. So if you imagine you have, let's say, a dome, and now it has, I don't know, 10,000 polygons, and then you want to reduce it to 1,000, then you need to, of course, find some points that would reflect or represent this curvature, but with lesser amount of resolution, like with a smaller resolution, right? So you're trying with this calculation always find those that would most closely imitate the source curvature. It's easy to stack levels of simplification, which can be relevant, for example, in LOD creation. And what I mean by this is that when we calculate this error, so like this diff from your original to your target geometry, it's a number essentially. Like this error is a number, right? So you can know how much you're off from your original one. So then when you need to even go lower, let's say you need to create another level of detail, it's still calculated knowing the offset from the original one, right? So that means that if we need to create 5 different LODs, each of them will try to be as close to the original as possible given the polygon constraint. Now I just want to mention this briefly. There's new method, like there was a paper in 2020 about probabilistic quadrics, which is a bit different way of calculating this error, but to be honest, this is a bit outside of my comfort zone to discuss. I just wanted to mention that there are still papers, even though this is established technique, there are still papers on how to make this calculation more accurate. Now, if we move forward, please, you can see this chair example, and you can see the difference, right? So on the left, you would have the high dense mesh, which is again well suited for close-ups, and this is probably how you create the asset, right? You're just modeling it, and you want it to be perfect. But then if you move to delivery, so if you want to show it to target audience, let's say your customers on your e-commerce website, then actually the topology no longer matters, because you're not going to edit this asset anymore. Like you just show it, right? So what matters is only essentially the beauty render, so like how it actually looks in the browser or on the mobile. But what lies underneath is not that important. So if you can see, while on the left the mesh looks like super nice and quad based, on the right it's triangulated and it doesn't look so beautiful and tidy, but the beauty is not that far off. Like the actual render, the real-time render, is pretty much the same as the source input, and you gain performance and you don't lose quality in this scenario, right? Like you just need to look good to your end user. You're not gonna edit this, so you're not gonna have a headache with editing those polygons, because you're not gonna do it. Now, if we please move forward, the final technique I want to mention is remeshing. It's also fairly old, I think, like also from the 90s. However, it's still being figured out. Now, I just want to mention there's small ambiguity in the word remeshing. Like it can mean two things. One is that you have your topology and you're just changing the topology on the same surface. But this is not what we mean by remeshing, at least not in this presentation. In this one, I mean reconstructing the geometry basically from the scratch based on the old one. So this is technique, like I mentioned, it's still being perfected. It's fairly slow due to the shrink wrapping process, and it needs a lot of accuracy. And then when would you use it? It's well suited when you have bad input. So basically your original geometry is not what you want, or it has a lot of tiny holes, and maybe it's a super complex asset, or you have the stacked layers. So I mentioned with decimation, stacked layers can be problematic because usually you care only about the external surface, in those e-commerce scenarios. However, those lower layers still can impact it, so can still intersect. In this scenario, it's good to actually like the remeshing is good to remove the invisible geometry. However, the downside is, again, performance can be a downside, but also it's hard to preserve data, for example, UVs, because like I mentioned, we're creating a new mesh and based on the old one. So we basically get rid of the data and we have to recreate it. The way it's being done, you create a voxel grid, like this grid that encapsulates your asset, and then we refine it, like you can see on those nicely drawn diagrams, and then you shrink wrap. So you basically take this shell that you created and you kind of try to match it, like you can try to shrink wrap it onto the original surface to reflect it as close to as possible to the old look, but with this new totally recreated mesh. And then there are some, it's difficult sometimes to find proper, in some extreme scenarios, it's difficult to find the proper points, so it can take time in terms of computation. And then you have very high dense mesh that's recreated, and then you would, on top of it, decimate just to get to this lower resolution target in the end. But this remeshed input will be much better for the decimation algorithm than just this messy, noisy mesh that you might have as your source. So if we move forward, please, there's again one example of a chair. So you can see, like, with those teeny tiny holes and like this weaker pattern, it would be very hard to decimate it properly in one step. That's why we first create this middle input, this remeshed input. So we create super high dense mesh, but it's already got rid of those teeny tiny imperfections, and they got baked to the texture to still preserve some look and feel of this pattern without actually having to have it in the geometry. And then you can see the decimated geometry on the right is just this triangle based thing, like you've seen in the previous one. And now let's please move forward. I'm going to briefly mention the animation because I think I'm running out of my time. With animation, there are also things we can optimize, and animation curves can be simplified. And for interchange format, it's common to convert the splines, for example, or some curves to high density linear curve, because there are different implementations of those splines and others that may lead into inconsistencies. And if you divide it into teeny tiny linear pieces, then you're safe, basically. Usually it's possible to compress this type of data very easily, or at least with a good ratio of the input and output. However, we are currently missing such compression in glTF, which maybe is worth mentioning here. Now there, as you might know, there are a few different types of animations. So with rigid animations, it's possible to simplify meshes. With skinned animations, when you do this, you need to have additional steps because you rebind the new mesh to the existing skeleton. Then with skeleton simplification, again, you need to have another few more steps because you need to redirect the weights to the bones that remain after your skeleton optimization. And then with shape keys or morph targets, depending what software you use and how you call it, then after simplification, again, we would need to figure out which vertex is affected by which target. And I don't want to go into more details because I run out of time. So let's please move to my final slide, which is this dancing Iron Man. Can you please play it? Thank you. So on the left, we have the original one. In the middle, we have, let's call it LD0 and then, or LD1 and then LD2. So you can see the poly count on those. It's 640K, 20K, and 5K. And you can press replay. You can see there's pretty much it's indistinguishable in terms of the movement, right? And those assets were optimized not only in terms of poly count, but also the animation itself was optimized. However, I would say it's basically indistinguishable one from the other. So you can see that you can save a lot of space and computation time for those real-time scenarios. And that would be the end of my presentation. And now I will hand it over to Max, our CEO, who will take you through material optimization. So next step in my high-level overview of asset optimization workflow. Thank you.
Right. Yeah, thank you, Paweł, for the introduction. So I'm Max. I have a background in computer science and 3D graphics, did my PhD and some research in that area, and then at some point started contributing to glTF, got super interested in the ecosystem, started contributing to the specs. And yeah, Paweł, I think, showed a really great deep dive into some topics related to meshes. So now, in contrast, I want to talk solely about everything that happens on top of the meshes, namely the materials. So yeah, thanks. On this slide, I just want to talk a little bit about optimizing textures in particular. And then later I'll have 3 more examples where I'll talk about material properties and extensions that glTF has to make our life easier there, then material variants, and finally, what if I don't use textures at all. So looking at this example, it's pretty common. It's the glTF flight helmet. To see that an asset that has been created by an artist comes with different kinds of textures for different kinds of materials. So here, for example, we have the leather of the flight helmet. We have the mask that has some rubber, and we have the glasses, the stand that is made out of wood. And then, for example, this little plaque down there that is some kind of shiny metal. And there are different textures to represent these details on the surface, and also different material properties such as roughness, or if something is metallic or not. Say, for example, the plaque is metallic, the wood is not, right? So they reflect differently. And then last but not least, the normal maps. And you can see the maps there here on the left-hand side. So there are 15 different maps, meaning 15 different pictures, storing information. And in the first row, you see the base color maps, most important. Then you see the ORM map. So that's occlusion, roughness, and metallic, all put into different channels of this one image. So the RGB channels, or the occlusion values, which is just a way to add some ambient shadows, basically. Then the roughness and the metallicness of the material. And then finally, last row, you see the tangent space normals stored in a normal map. And this is quite large. So we have a set of textures that leads to an asset size of overall 10.9 megabytes. And so what can we do to reduce that a bit without trading in too much of the visual quality? So one thing that we can do is using smaller textures, of course. So that's the no-brainer. We can just downscale them. And for many textures, that already works quite well, because you have to consider that an artist would usually not be obliged to think about it during creation time, right? An artist wants to get the best possible result, the visual result, maybe for offline rendering. And then if every texture is 4K, for example, that might just not work for real time. And during that step, we can also be a bit smarter and say, let's downscale things that are small in 3D a little bit more than we downscale things that are large in 3D. So we can consider the world space size of the surface where textures are applied. If that is something unique, then so if there's a unique scale for each texture, how it's used, and often that's the case. So that can help, and that already goes a long way. But then there's another issue. So if we have 5 different materials and we have all these textures here, they'll be bound to different textures on GPU, and every time we switch to a different material, we have to wait for the pipeline to switch during rendering the textures. And for one asset, it doesn't really make a big difference, honestly, if it's a small one. But in general, to be efficient with the rendering, we want to also optimize this further and minimize the number of texture switches, which helps us to save draw calls also. And that is especially important, of course, in bigger scenes. So if you think about, let's say, furniture in a floor planner or something like that, and you have not one asset, but 20 or more, that can make a big difference. So next animation, please. If we look on the right-hand side, here's an optimized output. We've just like optimized the texture maps, and now we have less than 3 megabytes, which is great for the web and also renders faster. So what did we do here? As you can see, on the top row, we have not 5, but 2 different maps now. And one of them has all the opaque parts, the other one has the transparent parts. So basically, we're using a different schema where on the left-hand side, the artist was basically deciding on where to apply each map based on like how the asset was modeled. On the right-hand side, we look more at how is the asset rendered. And during rendering, we differentiate between the opaque parts and the transparent parts, which need a different treatment and different settings for our shader and so on, and our pipeline, typically, so that we can have this nice alpha blending effect or like some transmission effect or whatever is done to mimic the glass, which is always a tricky topic in real time. And as you can see, maybe on if you look at the bullet points, we also use different resolutions here. And we use different resolutions in 2 ways. First of all, we use a bigger one for the opaque maps, so 2K for the base color and 256 only for the transparent parts, which are here only the glasses. And the reason for that is exactly what I mentioned earlier, that the glasses are relatively small in 3D. So we don't need to spend a lot of resolution there. And this way we get a homogeneous resolution over the whole asset, which makes a lot of sense usually. And so there's some dirt on the glasses, etc. But that dirt gets treated equally important as, let's say, dirt that I have on the plaque or on the helmet. So we basically take the world space size into account, or object space size. And the other rescaling trick that we did is that the ORM map has a smaller resolution. So the occlusion, roughness, metallic properties, often there are not so tiny variations in that, and you usually get a visually pleasing result, even if that map is not as large as the base color. So those are some things that we can do. And now, without actually changing the geometry, we got to a much more compact asset, which again transmits faster, but it also saves us GPU memory, which again for a large scene can make a difference and can come in really handy. And this is an advantage that is completely independent of how we encode the textures, right? Like, of course, if you have like texture compression, you can save even more GPU memory. Like we'll learn more about that later. So in Andreas' part, but yeah, just saying here, like if we reduce the images that we put into the pipeline, then we save in any case. Yeah, Andreas will also talk more about like this whole topic of how to compress optimally the individual texture maps with tools and standards that Kronos has helped to like create, which is really cool. So then in that sense, let's look at the next slide, where we look a bit more at material properties. So this is a really amazing example created by Eric Chadwick, where you can see that this olive dish has like this glass cover that shows different kinds of cool effects that are usually hard to mimic in real-time renderers. So one of them being that the olives look a bit distorted visually, like they look like they get enlarged a little bit here and there. And that is an effect that can be realized with the transmission extension and then and volume. And on the other hand, you have some iridescence effect. So, and IOR. I forgot IOR, so you see the listing down there where it says extensions used. So the glass uses those 3, transmission, IOR, and volume. And then the iridescence effect is done with the respective extension that's just called KHR materials iridescence. So that's this like rainbow-like shiny effect on top. And you can actually see on the top right-hand side some photos of the actual physical object, and they see that this effect is super strong. So not having it on the virtual replica, on the digital twin, if you will, would really have us missing something that's super important for the appearance of this object. So luckily, with all the material extensions that Kronos has brought to glTF the last 2 to 3 years, we can get a pretty good result. And it's worth noting that here, like, it's also important to prepare the asset accordingly. So for example, you have here as you can see, like the normal map. So if you look at the 6 images on the bottom right-hand side corner, then there's the normal map, but there's also, for example, a thickness map, which we need to get the correct effect for the refraction inside the glass. So usually we could cast rays and see where they end up and how long they travel before they hit glass again and so on. In real time, we can't do all of that, at least not in the common WebGL pipelines, how they are implemented with a rasterizer. So instead, we really fake this and basically calculate in a shader where would our ray of sight roughly go if the material had the thickness, etc., and how would it affect what we see here on the front, etc. And so these maps need to be baked accordingly. And so even if the asset doesn't look as if it would have a lot of texture applied, these are some utility textures that we need to use. And in the same spirit of looking at the extensions and how textures are being handled in extensions to achieve a better visual result or a more compact result or something that's more flexible, I want to show another example in that direction. So next slide, please. Thanks a lot. Which is the KHR materials variance extension. So here you see 3 different colorways, as they say, of one shoe. And these colorways, called street, beach, and midnight, could be imagined in a web viewer configurator, right? We can just cycle through them, and they all share the same geometry. They are also all stored in a single glTF binary file, single GLB file. And what we can do here is reuse the base color. If applicable, we could even reuse the ORM maps, or we can reuse the normal map. And in that case, the only thing that really varies is the base color. So we're reusing the normal map and we're reusing the ORM map. And that comes in quite handy because, again, we have a more compact asset, but also it can be quite useful to know that all the data of my 3 variants is stored within this one GLB file, which is just a nice thing to have in many applications. And I transmit this file once and have them all ready. So I talked a lot about textures now, and I want to conclude this part with the last example. Next slide, please, where we have actually taken away all the textures. So here on the left-hand side, you see textured object, 6.5 megabytes as an input asset. And sometimes when you want to have a really fast loading, sometimes low resolution preview to show an AR, for example, really quick after less than a second, less than half a second maybe, or you want to load a lot of objects in a floor planner really quick and show a room instantly after loading, be able to move everything around, or show something quite in the distance, in a sense of level of detail, as Paweł mentioned it, then it can be useful to just say, hey, can't I just drop the textures completely? And then there are 2 ways of how you can do that and still represent the color somehow. One being vertex colors, which allows you also to use a single draw for the entire object. You can have quite some variation still. Or material colors, saying okay, I just use either a palette texture, or I use different materials as just different, basically vector values for each base color, for example, and apply them during rendering. So really simple. And as you can see here on the right-hand side, the result that we got here by just taking the average texture values is even less than 30 kilobytes, which is quite nice. For this particular example, also looks pretty good. Of course, depends a bit on the asset. And that's just to show that we can also get quite far sometimes by even not using any textures. So with that, I'd like to conclude my part and hand it over to Andreas to talk more about how to compress textures and do a lot more cool things with Chronos tools.
You're on mute, Andreas.
Yep, and I'll start. Yeah, so first of all, a short introduction about myself. I'm Andreas Vasilakis. I'm co-founder and CEO of Phasmatic. I have also a computer graphics background. I defended my PhD 10 years ago with focus on geometry processing, photorealistic rendering, and interactive graphics. I have also the honor of serving as adjunct professor at Athens University. Yep, Phasmatic. I co-founded Phasmatic a year ago, which is a Greek deep tech startup company that pushes the boundary of photorealistic 3D graphics on the web and augmented reality. And I think that's enough about me. So let's dive into the 3D artist workflow bottlenecks and discuss how we can build solutions that can help artists in order to accelerate their process. So authoring content for a glTF format can be exciting, but at the same time scary if you're not familiar with creating assets for 3D web and augmented reality. And because glTF is designed for real-time delivery, meshes should also be created with real-time rendering guidelines in mind. So both Max and Paweł already talk about best practices and specific guidelines in order to prepare assets in this case, and also offer optimization techniques, several of them. I will also want to mention that there was a Chronos glTF webinar conducted approximately 2 weeks ago by Eric Chadwick, which will talk about the artistic creation of realistic PBR materials. So I'll tell you not to miss it. You can find it on the official Chronos Group YouTube channel and dive into to see more. So how we can then optimize the 3D content even more without compromise the visual quality in the glTF files. We can perform optimization. So yes, we can optimization can efficiently be achieved via geometry and texture compression in glTF. And I will share more details in the next couple of slides about it. But are we done? We can press the button and say, yeah, perform geometry compression or texture compression, and is everything okay? No. Quality assurance has also been performed in order to ensure that the content, the final glTF compressed content, is error-free, of course, visual accurate, and meets the deployment standards before publishing. The standards that also Paweł talked about it in the beginning of the talk. Yeah, but how 3D artists can perform both compression and after compression, then validate the results. The common solution is that you compress and then validate. Exactly how you can do the compression. First of all, you can compress using command line interfaces from several APIs that can offer you this functionality with scalability. For example, glTF Transform API does a very good job on this process. Secondly, all well-known digital content creation tools offer compression, also with tuning, when you choose to export into a glTF format. Blender is a solid example, which I'm aware that exposes this kind of functionality. But generally, these kind of solutions lack of intuitive visual inspection and validation mechanisms. What you have to do, you have to compress, you have to, let's say, create the 3D model, then you compress, you export, and then you have to import in order to check the differences. So in a way, we need solution in order to ensure compliance and preserve the essential information of the final 3D model. So you can imagine that all this process requires a tedious 3D model reworking, which eventually will lead to an avoidable supply chain friction and increase company costs. What can we do about it? Yeah, we need tools that can be interactively, maybe can be scalable ones, but yeah, we need tools in order to enable artists to improve and streamline the creation of 3D assets that can be easily be used for real-time rendering on or offline rendering on multiple publishing formats. Yeah, most of the cases real-time. And Kronos has created 2 online solutions to help towards this direction, which I will talk in detail in a little bit. It's the glTF compression and the glTF asset auditor. But before talking about the tools, we have to talk about how glTF natively can support compressed geometry and texture through the use of key glTF extensions. The most well-known one in the case of the compressed geometry is the Draco. Draco is a high-performance library developed by Google that's specializing in compressing and decompressing 3D mesh data. How it efficiently reduces the size of the mesh representation while preserving the visual quality and accuracy of the 3D model. glTF supports the use of Draco? Yes, it does. It can compress the geometry data of the 3D model in a way that instead of storing the mesh data in its uncompressed form, well known as position, normals, and texture coordinates, it references the compressed Draco version of the mesh. So here is an example. We have a horse metatarsal 3D model that has been compressed with Draco using the Blender glTF exporter with the default compression settings. I didn't change anything. And you can observe that we have a significant file size reduction without impacting the visual fidelity. Yeah, we can do that very easily, but we can, yes, of course, gain a lot. Of course, reduce file size and faster transmission over web, but we have to keep in mind and remember some limitations. The first limitation of Draco is that it requires additional processing because you have to perform decompression before loading on the GPU memory and eventually render the 3D model. So it will add a slight delay. Second issue we can say is that Draco can only be used for optimization on common mesh attributes like vertex position, normals, and texture coordinates. It's not effective so much in other not standard data like animation, for example. And last but not least, the size of the decoder of Draco library may outweigh the size saving if the geometry is less than 1 megabyte. So keep in mind that if you want to compress this very small size 3D model, it's not wise to compress it using Draco because the whole library is larger than the gain that you're gonna have using the Draco compression. In contrary, there is a second solution. Instead of Draco, we can use the mesh optimizer. Mesh optimizer focuses in a different way compared to Draco. It tries to perform optimization on the mesh in a way that aims for optimal GPU rendering rather than achieving optimal compression ratio. So it succeeds that by performing several optimization techniques such as vertex cast optimization, vertex quantization, index buffer optimization, in a way to reorder data and quantize mesh data to minimize GPU memory access and improve cache efficiency during rendering. It's focused in a similar way like the KTX for texture compression that I'll talk in a bit. So yeah, we do not perform the best compression, but we have the best rendering times when we want to perform mesh compression. Before moving to the texture compression, I want you to say that geometry compression is generally lossy. So as Pavel showed, the compression process should generally be at the last stage of an art workflow. And also uncompressed original files should be kept. Yeah. So when it comes to texture compression, KTX format Chronos texture format, meaning is the golden standard, of course, because texture in a glTF file can be compressed into GPU textures using basis universal compression, which, similar to mesh optimization, meshopt, offer faster GPU upload and less GPU memory consumptions than the PNG and the JPEG textures. So PNG and JPEG are fully uncompressed when loaded in GPU memory, but KTX stays compressed on the GPU. So, for example, on the left, the stained glass lamp model from Wafer uses JPEG and PNG textures, and the overall file size is about 13 megabytes, but it increases to 96 megabytes in GPU memory because the textures must be uncompressed to use them for rendering. While at the right figure, the lamp, it's compressed with KTX. So you can see that the artifacts are nearly impossible to see, but the savings are very drastic. So we reduce the file size to 10 megabytes and it becomes 21 megabyte in GPU memory, which is a huge gain when we're talking about frames per second. So how we perform now compression using the KTX format? There are two methods, the ETC1S and the UASDC. ETC1S is very useful when we want to perform texture compression and focus of texture compression, meaning on file size, while UASDC offers higher visual quality. Yeah, but again, the problem is how we can choose in different texture types which basis universal compression method we will use, ETC1S or UASDC. It can be three options. First of all, compress all textures with UASDC. This can produce, of course, a larger file size, but usually shows less compression artifacts. In the contrary, we can compress all textures using the ETC1S. This will produce the smallest file, but it will create a lot of artifacts. What's the best solution? Mix both of them. Compress, for example, normal and occlusion roughness metalness texture using UASDC in order to keep more details, while you can compress using the ETC1S for all the other textures, basically diffuse texture, where there are large areas of solid colors or mostly monochromatic values on this. So we will not add a lot of compression artifacts in the end. For more details of how and what choices you have to perform when you want to perform KTX compression for your texture, you can refer to the official Chronos KTX artist guidelines. But again, how you can perform all this texture compression? Yeah, one way is perform using scripting and compress that, but we need interactivity. So Chronos released the open source glTF compression tool very recently, introduced at SIGGRAPH 2023, where we can optimize and fine-tune texture compression in order to help artists adjust their 3D assets for optimal web delivery. What was the idea? What the focus of the glTF compressor tool? Before I move to a live demonstration, I would like to highlight the core features and the ideas behind the tool. Of course, is that we allow users to initially create very incredible, detailed, and realistic assets without having to set up how this asset will perform the web due to the large texture sizes. So we let them upload their file, upload their model, and after loading of the tool, we can observe the textures as displayed as thumbnails with together detailed image information such as the format, resolution, file size, usage, and estimated GPU memory size. And then after that can batch select or independently select textures in order to compress it in a particular way. We allow them to compress textures using the basic formats, such as JPEG, PNG, and WebP, but of course, we add KTX support in a way that can offer the best and relieve all the possibilities that it can do with KTX. So we add advanced compression options for this targeted format. So yes, let's say artists compress a subset of the textures, and then what's the biggest gain here is that the artist can carefully inspect the quality of the compressed images in a split view. So they can do it both in 2D and into 3D. So we allow to check side by side how the compression was performed, if you like it, if you want to recompress it again and again and again until you have the best quality or the best file size that you want based on the publishing target or the use case that you have. And in the end, you can export the optimized assets with a newly compressed textures. So in terms of development, the glTF compression was built on top of the well-known Kronos open source tool, the glTF sampler viewer, which is basically a viewer for glTF files. And in its current form, yeah, it includes only texture compression, but geometry compression capabilities are currently developed and will be added in time. I think it's going to be officially implemented by the start of the next year. And I'll now move to the live demonstration. So here, if you're aware of the glTF sampler viewer, you see that nothing changed except that there is an extra button here. Yeah. So, for example, let's see the avocado. Here's a texture compression button. And when you press it, you can see all the textures that this model has with name, type, usage, compression. Yeah, compression is not yet done yet. Format, resolution, disk size, and GPU size. Then you can select which one of them would you like to compress, or select by type. And the benefit when you select by type is that the KTX default settings for each type is chosen by the best KTX compression method that's best to use. Of course, you allow you to change that, but for example, for normals, it's best to keep the details. So you want to perform the compression with UA-STC compression method. So let's try to compress all textures using KTX with default settings. And also I would like to downscale a lot the textures. Let's say, don't try this at home, of course. Yep, and after the compression, you see two kinds of things. Yep, we have new information about the total texture size before and after the compression, yet we gained a lot, gained almost 7+ megabytes. But in the same time, we can check if the compression was, how much visual fidelity we lost after the compression. So in this case, where we can check that, yeah, it's not the same. Yeah, this is logical because we downscale a lot the texture resolution. And yeah, you can zoom, you can check it on any angle. Yep, but you can also perform the same comparison in 2D level. So you can select each texture you want and check the details in the same way, or even zoom, check pixel by pixel. Of course, after that, you can export your glTF, the compressed version of the glTF file. Last but not least, yep, we will not forget that Kronos Group has also released the open source glTF asset auditor tool in order to artists include it to their validation pipeline. And what this tool does is that allow you to compare the characteristic of the 3D asset against a preferred or predefined ranges that is defined in an audit profile file. So an audit profile can define a lot of characteristics. For example, right now it has almost 20 that can be checked in order to help enforce best practices and ensure that the asset that you are creating fits to the usage or in the specific use case that you have designed it for. So some of these characteristics are file size, of course, triangle nodes, material nodes, mesh nodes, texture dimension, and others. So the default audit profile contains best practices recommendation specific for the 3D commerce, let's say, domain, as published by the official 3D commerce working group of Kronos. But the tool is not restricted in order to use only this audit profile. Or creators or artists can author custom audit profiles in order to match their own requirements and use cases. So in terms of usage, the glTF Asset Auditor is available as a browser-based front-end implementation, similar to that you can upload your file and then you get information about what crashes or not on your file based on the audit profile that you have selected. Or you can use it as a command line interface to enable asset validation at scale. I think I covered most of my things, and I will pass to Adam to shed some light about the optimization work they are doing at Cesium. So Adam.
Thank you, Andreas. So let me go ahead and share my screen. Okay. All right, so I'm Adam Morris. I work at Cesium, and I have a master's in human-computer interaction concentrated on XR technologies from Iowa State. I've been a core team member of the 3D Formats Working Group for several years now, and I've been a fan of glTF for longer. I've also been lucky enough to have worked on the AR features in an app that a good portion of the Americans in this webinar today have used if they shop at Target. So today, my colleagues have talked a lot about the intrinsic optimizations that we can do for glTF. Let's talk about some of the extrinsic optimizations that can be done. How you organize and render a scene based on your glTFs is of equal importance to how you actually optimize them individually. So the real question is how do we get from a single model to handling really highly detailed scenes? So to do this, we're going to look at 3D tiles, which is a tiling format based on glTF, and it's kind of the bread and butter of what we do here at Cesium. So 3D tiles is an open standard, and it's currently the leading standard for streaming 3D geospatial data. It was started by Cesium in 2015 and is the brainchild of Patrick Kazi, and it's been an OGC community standard since about 2019. 3D tiles, it can be used for geospatial applications, but it's not just for them. You can use it for point clouds, CAD BIM, highly detailed models, and we've even seen it used for fractals. This isn't an exhaustive list. If you think that 3D tiles might be useful for your application, we do encourage you to try it out because it does allow for streaming large amounts of data like I'll be showing you today, very, very efficiently. So it's made up of three major components: a spatial hierarchy system, glTF models, and then at each leaf, and then a metadata system. The spatial hierarchy system is kind of essential to how we allow for a very flexible hierarchical level of detail. And today I'm going to talk to you about how that hierarchical level of detail works, so you can optimize your own rendering. Before we get started, I do want to touch on some of the basics about octrees, quad trees, and KD trees. Many of us have seen these before in our computer science classes when we were going through school, but it's always good to have a little bit of a refresher. So likely most all of us here are familiar with octrees because these have been the go-to standard for 3D graphics for decades. They're three-dimensional. They extend a quad tree, which we'll talk about a little bit in a moment, by using 3 orthogonal planes to subdivide a space into 8 children. They're really useful for non-uniform subdivision or tight bounding volumes. If you have overlapping children, it's very, very efficient. There are many cases where the extra complexity, though, is unnecessary, especially when you're dealing with terrain data or any sort of kind of flat plane of data. So we're going to talk about where it makes sense to use an octree and where it doesn't. Quad trees are the siblings of octrees. They're 2-dimensional as opposed to octrees 3-dimensional. Each node has exactly 4 children. The regions can be square, rectangular, or any arbitrary shape. There's actually some further optimizations that can be done around bounding volumes for each child, which is really efficient for sparse sets. And then there's loose quad trees as well, where you've got children that overlap and coherence is preserved. This can be useful to prevent specific 3D models from being split across partitions. And then, you know, a real good example of what I mean by tight bounding volumes and then overlapping partitions can be found here. So if you look at the blue arrow here, you can see that there's kind of a sub-bounding box within that outer bounding box. And that inner bounding box actually has those blue buildings. Then we've got on the right side, you can see a quad tree that's got overlapping partitions, and there's 2 bounding boxes there, one with pink buildings that's being pointed to kind of on its own, and then the green buildings with a green arrow pointing at them. The red arrow is actually pointing to an outer bounding box that surrounds both of those inner bounding boxes. So what this allows is, if you look closely in the center where that green arrow is, you can see that the pink building that's in the center and the green building that's in the center, they kind of bleed into the other boxes, but not completely. And so this kind of allows you to kind of keep that coherence. Yeah, so. Finally, I do want to just make a mention of KD trees. We're not going to dive deeply into this today, but they are useful for subdividing sparse and non-uniform data sets. They're really useful for point clouds in particular. And they actually have their roots as a special case of the old school binary space partitioning trees. They're a binary tree where every node is a k-dimensional point in space. Each node implicitly generates a hyperplane that then divides the space into 2 partitions called half spaces. And it's got non-uniform subdivision, so it allows for a little bit more balanced tree for sparse and non-uniform data sets, which is where the real usefulness for point clouds comes in. You'll also note that there is the curse of dimensionality, which I'm sure we've all heard about when we learned about KD trees. In graphics, it's largely irrelevant since K is generally 2 or 3. That becomes more of a bigger issue when, you know, the data science people are using KD trees. You can also do some further optimizations, and I want to make a special call out for multi-way KD trees. And I have a link in the slides, and after the presentation, if you look at the slides and click on that link, it'll take you to the paper. That can be super useful for really, really dense point clouds. So, and I just want to stress, you can use a combination of methods. You don't have to use a single method. And in fact, with 3D tiles, that's actually what we do. We use a combination of octrees and quad trees based on what's going on. So for our bounding volume subdivision, for example, you can see that we've got a root box here, and then you can either use a quad tree or an oct tree, and this is how it kind of is stretched across the globe. And this is an important step because once we know how we're going to split our bounding volumes, we can then, basically move on to kind of a deeper level of what's going on. So it's important that you choose the right subdivision too, because in the case of like when you're dealing with large terrain data over kind of a wide area, for example, 3D maps and that sort of stuff, it's really useful to use global coordinates or quad trees for global coordinates. Then when you get in closer, though, it can be really useful to use an oct tree for local coordinates. And mixing and matching, that's really the real optimization here is be ready to make a judgment call yourself on what you need to do. One of the things that I will say is that a major advantage of quad trees is the uniform behavior, which is really why when you are dealing with global coordinates, they just are the right way to do it. Because, and we'll dive in a little bit deeper to that, but it allows you to actually start to mix detailed levels based on camera distance and that sort of stuff. So this video here, you can actually see us using a hierarchical level of detail if the video will load. That's, is it gonna load? Well, hopefully it will load here in a moment. Sorry about this. Not quite sure what's going on.
Adam, I can try.
There we
You want
go.
me to?
Nope. It's working now. Okay, so my apologies. This hierarchical level of detail and mixing the right methods and everything allows us to stream and render very highly detailed models like the spatial discovery here. This shuttle is actually a 3D tile set. It's actually 1.9 gigabytes. Since it's a 3D tile set, the user's machine never actually has to render the full 1.9 gigabytes at once. Untiled, the model is a 2.2 gigabyte file, and as you can see that there's a little bit of pop-in that's occurring as we zoom in, but the detail, especially the textures and the mesh geometry, gets much higher detailed as we zoom in here. So and this is the kind of advantage that you can have by using a hierarchical level of detail. And I will say that this is using a quad tree in this case, and then the terrain in the background is actually using a I'm sorry, this is using an oct tree, and then the terrain is using a quad tree. So misspoke there. Okay, so let's go ahead and jump back a little bit and discuss how we handle coordinates, as that's kind of a critical piece here. In 3D tiles, there's basically two ways to handle tile coordinates. All of these coordinates are zero indexed, with 0 representing the implicit root tile, and then the value going progressively higher for children. So 0's children are 1, 1's are 2's, etc. For oct trees, we use a level XYZ coordinate system. For quad trees, we use a level XY coordinate system. I'm going to focus on quad or oct trees here because it's relatively easy to derive the system for quad trees. If you understand oct trees, just take out one of the dimensionalities and you've basically got it. In this diagram here, we've got a bounding box volume that shows our coordinate system. Note that the first value represents the level, and then we have the XYZ coordinates. In 3D tiles, since we deal with geospatial a lot, we also have a way of handling larger regions that are using what are creatively called region bounding volumes. The main difference between the box and the region is that the region actually defines what the axis corresponds to. In our case, X is west to east, Y is south to north, and Z is altitude. Here we have an oct tree representation of a WGS84 ellipsoid globe, and you can see that the XYZ orientation is overlaid. The outer red box is the root implicit tile, and then you've got subdivision in each individual intersection with its coordinates. Handling coordinates this way can also be helpful when you're dealing with global or even open world game scenarios. And picking the right level of detail at the right time is equal importance to how you structure your data. In 3D tiles and geospatial, it's really important for us at Cesium to always precisely represent the error, known as geometric error, introduced when we're using lower levels of detail. And so the geometric error, it specifies an error in meters for simplified representations of the tile's geometry. And then that is derived from metrics such as point density, mesh or texture decimation, or other some relevant metric to your tile set. In the case of most 3D tiles, I would say we always do basically point or mesh density. The geometric error is computed when the hierarchical level of detail is created, and then it's agnostic of the runtime. So this is something that's done ahead of time and then stored. And then at runtime, what we do is we translate that into a screen space error. And that quantifies basically how much of the geometric error will be visible in terms of pixels on the screen. And so when the screen space error exceeds the threshold, the runtime will then pick a higher level of detail. And renderers can actually set a maximum allowed geometric error based on their own parameters. So on a mobile phone, you can actually limit the maximum geometric error at a point in time to a value higher than on a high-powered desktop. Once the maximum is reached, you're not going to get any higher levels of detail that'll be loaded. And this combination of geometric and screen space errors allows developers at runtime to pick the detail and quality that best suits their needs for their applications, workflows, and devices. And this also allows for a heterogeneous mix of tiles. So in this image, you can see as the camera closes in, there is basically a mix of tile detail levels that are being loaded. In particular, note that the band at the bottom of the screen is a mix of L15 and L14 tiles, with L15 being a higher level of detail than L14. Since the geometric error is for the tiles on the right of the image is sufficient for the highest possible detail, they're loaded. I'm sorry, on the left of the image is sufficient for the highest possible detail. The loaded in is L15. More detail is potentially visible in the center and the left of the image. I'm sorry, I mixed that up in my notes. Okay, on the right side of the screen, we've got L14. The highest geometric error that we can get there is L14, so that is sufficient for our needs. When we look to the center and left of the image, L15 loads in to the geometric error for those tiles. So since those are slightly closer, even just very slightly closer to the screen, we can actually see basically the higher level of details there. So let's kind of start to put all this together. By intelligently structuring our data using the right data structures, we can optimize our loading and streaming performance, even in power-limited systems such as mobile devices and VR headsets. Rather than loading everything up front, we can intelligently load and unload the data as needed. This is really the power behind 3D tiles, but optimization shouldn't stop there. When we start to involve some sort of compression, such as Draco, like was discussed earlier, we can reduce this size even further, albeit introducing a little bit of CPU cost to handling the compression. So this graphic here is a scene within Liverpool that is in Cesium.js. And basically, you can see the before and after here, compressing a single tile set with Draco. And this is this is very, very highly detailed, even with the Draco compression. And the source image is about 1.6 gigs. The uncompressed 3D tile set is 1.2. When we add in both KTX2 and Draco compression, we drop that down to 482 megs, which is a lot more palatable if you're dealing with some very, very low-powered device or that sort of thing. And it's important to mention that that 482 is the total size of the tile set. That is not at a point in time what's going to actually go over the wire. What's going to go over the wire is significantly less than that. So each tile then could be only a couple hundred K as opposed to a couple hundred megs. So there's some notable glTF extensions that I also want to call out that are useful for glTF optimization. Obviously, the Draco mesh compression, which was discussed earlier today. I also want to call out mesh quantization. We use that a lot at Cesium, and it's very, very useful. We also use mesh op compression a lot as well. It's not quite as good as Draco, but it can be very useful in some scenarios, such as terrain and that sort of stuff. And then, of course, the mesh GPU instancing is very, very powerful as well, especially if you have a model that's going to be basically repeated many, many times within a scene. I also want to call out a notable mention for the Microsoft LOD extension. It doesn't have widespread support, but it does provide an alternative method for adding level of detail to glTF files. And it's baked into the format as well. So if you'd like to learn more about some of the stuff that we went through today, I'd encourage you to check out these links. For glTF, of course, there's the glTF GitHub page. And then for 3D tiles, remember you can use this for more than geospatial. We do have people out there who are using 3D tiles for various engines that are not our own engines. So Vulkan Scene Graph now has something, and then 3JS has an extension that is managed by NASA. Also, I want to just say that, you know, like all of our extensions and all of our code at Cesium is open source. So if you want to use us as a reference in your own implementation, feel free to use it. Otherwise, you know, if you're using Unreal, Unity, Omniverse, or even JavaScript, you know, I'd encourage you to check out our engine, and yeah, hopefully it will be able to help you out. So yeah, I guess we're going to move on to the Q&A next, and yeah, I will pass it off to Max.
Yeah, and before we get there, if we can have the speakers turn on their cameras. And Max, as we're transitioning into the Q&A session, I understand that DGG is hosting 3D Pipelines Days. Can you give us a little bit of information on that?
All right. Yeah, thanks for asking, Jeff, and thanks for also Kronos' interest in this event. So just like we do today here, we are bringing together speakers to talk about different topics related to scalable 3D pipelines. Optimization will be a part of that. And there's an event page where you can see an overview. So we'll have also people that are very active in the community, such as Felix Herbst, as you might know, like from Needle Tools, people from industry, but also like, yeah, people working in standards. Eric Chadwick, who created this beautiful lamp model that we saw a lot of times now, will be there and speaking. And we'll also have someone from Fraunhofer talking about nerves, for example. So it's a very tech-heavy event, and in that sense, thanks for asking, and thanks, Kronos, for sharing this. Looking forward to seeing many of you there, and we'll also share after the event some of the recordings where the speakers consent on YouTube for free.
Wonderful. And then we're having you go ahead and host the Q&A session, or would you like me to?
I can do it.
Okay.
Thanks. So there's two like at least two questions I'm seeing. Like one live question coming in from VoxVN, saying, I would like to know if we can expect a general light map extension for glTF. Right now, different engines build extensions with specifics for their engine only. An interoperable standard would help make use of this technique on web, in addition to Blender glTF export support. Yeah, so maybe just looking into the round, if there's anyone who would be interested in answering this particular question about light map extension, light map support.
I mean, I can take a crack at it. I know it's in the roadmap. It's a matter of, I think, getting it done. There has been interest, and we know that there is community interest, but it's just a matter of prioritization and getting to it. So the answer is yes, eventually. I just don't know when it will be is really the best answer we can give you.
Right. Thanks. And any addition from Andreas or Paweł?
I think you can hack it somehow. That's the best solution right now. Yeah. Sorry. So if you have an empty slot in the in the image in your material, then yeah, you can somehow place it if you use Blender, for example, and place your baked texture. And yeah, of course, you have to have a specific a render in order to somehow import the texture, have a custom renderer, and visualize the effects that you like. For example, you can mix the diffuse and indirect, the direct and indirect light map that you may have, and multiply it into shader, and and avoid the lighting from the environmental lighting that you have. So you can say that the glTF file is unlit mode. So you avoid all the lighting since you have baked all the light information into your textures.
Yeah, and I do want to make a call out for basically the EXT Lights IES extension, which might kind of fit your need a little bit. They're IES light profiles that you can use as light sources within a scene, so they'll at least be consistent. And then, of course, there's the image-based lighting extension that is a vendor extension as well. But I don't really know the state of that right now in terms of support. I know that people are using it. I just don't know where exactly that stands today. Both of those extensions are vendor extensions, but they are supported, and there's a fair number of engines that support both of them.
And I can add to the Blender support that once we actually have this light map extension, it will most likely get to Blender as well, because the glTF IO plugin for Blender is supported by Kronos Group, and we had I actually led some efforts a few months back to include the support for the latest extensions and basically make it more robust. So if this one makes it finally through the roadmap, then we'll for sure have next iteration of new extension support to Blender IO. So once it's done, it will be also supported in Blender.
Great. Yeah, thanks for answering. We're open for more questions, looking forward, and while collecting more, going to the next one here, just asking, is there a specific way to optimize assets for the browser, or does it depend on the application? Yeah, I guess maybe we can answer that with more than just yes or no by giving some examples.
Yeah, I can start maybe, unless you want to take it, Max, first.
Oh, please.
Okay, so I would say for the web browser, like with many things, you need to use common sense. But if you're targeting web browser, it means that most likely you don't really know your end device, right? So because if, for example, you target a specific, let's say you target iPhone Pro for some reason because you do just stuff for Apple, or maybe you're targeting a VR headset, and you roughly know the spec you're aiming at. But with the web browser, you can pretty much run it on anything, right? Which means that usually the common sense would be to try to get as low as possible with some things like bandwidth, for example. So compression can be a good tool, so to speak, to pick. Because if you care about bandwidth, then the size of the file might be more relevant than this initial, I don't know, half a second or a second that you would lose on your end device for the decompression, right? Because then the internet bandwidth is important. So I would say in this case, size over processing speed in the end, maybe. Then again, draw call reduction is super important as well in this case, because again, if you're targeting web browser, it means you're targeting whatever device. It can be 10-year-old laptop, it can be some low-end mobile device. So for web browser, I would say you want to go as low as possible with many things. And then on top, of course, if you're able, in some cases, in some applications, if you're able to maybe detect the hardware you're running on, then you can have the replacement asset for a bit better quality for those higher end devices. So that can be an option. And there's also actually some discussions in Kronos about the extension to support it more natively, so to speak. But yeah, I know it's a fairly generic answer, but that's the best I can get you in terms of web browsers. Like you don't know the device with the web browser, so try to go low with whatever you can. Maybe someone wants to add to this.
Yeah, there is no golden standard. Yeah, of course you have to optimize the file size and delivery, since the optimal goal is the customer experience, the user experience. So you, of course, don't have to make the user wait. So the most important part is get the 3D asset in as low as possible file size, but also do not destroy the visual fidelity of the asset. And then you can, in the background, load the actual original file size and blend it in a way that is not visible to the user. So you keep the experience in a way that keeps the user in mind, keeps the user on the target. So yeah, what's the best solution in order to do that? Yeah, you have to perform create several LODs, and then start loading, start deciding which one to load based on for example, the device that you are trying to load or deliver the asset. And if you know that the level of detail can handle by this GPU or this mobile or this desktop, yeah, it's going to be loaded and it's going to be rendered in real time. Yeah, so you can offer this kind of solution. But if you know that it's going to be rendered in a commodity hardware in an old mobile phone, then you have to be prepared, and you have to optimize it, even with a robust solution, as Pavel talked, or with more aggressive, as Max discussed about it, throw away all the textures, and yeah, then you got the model, then you got the experience as smooth as possible.
Yeah, thanks, Andreas. I would like to just add myself to that answer, that like just as a detail, right? Like if you have a specific application, then it makes sense to really like keep in mind what happens during runtime in an application. And for example, like very simple example, you have like a little cupboard or like something that has like, let's say, drawers, and maybe you have a single item view and you open the drawers, you can look inside. So there's an animation, or you can like hide or configure the doors differently. Then that affects directly how you set up your asset, right? Like, for example, if I cannot open anything, I can just throw everything that's invisible away, right? I can just throw away everything that's on the inside. But if I open it and like I have an animation, and of course not, and then I also have to check like how's the animation implemented, right? Like which nodes are like being animated with a transform, so these need to be separate. And also if I want to exchange something during runtime, these primitives for rendering also need to be separate, so that I can exchange, let's say, the handles on it, if I have a configurator for that, and so on, right? So the runtime really plays a huge role. So that, as Andreas said, there's no golden standard, right? It really depends on so many factors. But that's also why it's a fun topic. And there's another question here. I kind of went into that direction already, like saying, is there a specific way to optimize 3D avatars, and is mesh decimation the best solution? Yeah, I don't know if would be interested in taking that one.
Well, since I talked about decimation, I can take it. So I would say yes, mesh decimation is the best way to go about it for the reasons I mentioned during my presentation, which is with decimation you're able to preserve data. And I called out UV layout specifically, but it's not only about UV layout; it's also about the animation weights, like the blend weights, and then all the animation properties that have to do with the existing geometry, right? So maybe when you have just sorry, if you have let's say simple animation when you just like move boxes around, and then it doesn't matter, or like when you have two objects and like you have rigid animation and they're independent and you just have like move, then it doesn't matter because you can still have two objects and rigid animation can be still applied probably if you do it properly with remeshing. However, with anything else, like with the skin weights or basically any character animation for that matter, if you do the remeshing, then you have new mesh, so you don't have the old data, right, in the most scenarios. So, and with the decimation, you can still translate this old, for example, weights to and the skeleton and rebind it. So yeah, that's why decimation, since you can preserve some data during decimation process, it would be the way to go.
Wonderful.
And
I think that's about the time we have. Thank you, gentlemen, for a wonderful webinar. We appreciate all your time and effort in putting it all together for us. As a reminder, a recording of this presentation along with the slides will be made available on the Kronos Group website, and a direct link will be sent to you in a follow-up email. We also have some upcoming events that you may be interested in. In addition to DGG's 3D Pipeline Days, October 12th to 13th, we have a next webinar. October 17th will be glTF Complex Scenes and Interactivity. On October 31st, we'll have Let's Get Moving, Adding Physics to glTF webinar. Kronos will be a sponsor and have a booth at the Blender Conference that will occur October 26th through the 28th. So come join us there. And on November 14th, we'll have the Standardizing Body Attachment Points for 3D Commerce Virtual Try-On webinar, which should be a really good one. And as you leave the webinar, please take a moment to fill out the survey that pops up. Your feedback is important to help us improve these presentations, and please let us know if there are any other Kronos-related topics you may be interested in. Thank you for joining us. We hope you enjoyed the webinar and have a great day.